Welcome back to this video, guys. In this session, we will talk about model evaluation and hyperparameter learning. Okay, so after training a machine learning model, it is crucial to access its performance and make improvement. We will explore key techniques for evaluating model accuracy and how to turn the model hyperparameters to achieve better results. Okay, so let's have an overview. Before we jump into hyperparameters tuning, let's first understand how we evaluate our machine learning models. There are several metrics that we use depending on the type of problem, classification, or regression. Okay, so accuracy, the first problem is accuracy. The ratio of correct prediction to the total prediction is useful for balanced data set. Okay, second is precision. Precision, the proportion of positive prediction that were actually correct. This is especially improvement when false positives are costly. Then we have recall sensitivity. This proportion of actual positive cases that were correctly identified by the model. It is critical when missing positive cases has higher cost. Then we have F1 scores, the harmonic mean of the precision and recall. It balances both metrics, and it's often used when you need a balance between precision and recall. Then we have AUC-ROC, the area under the receiver operating system, operating characteristics curves. This matrix is useful for evaluating classifiers, especially when data set is embedded. Okay. Additionally, we cross the validation to access stability of models, performance across the different subsets of the data set. It helps to ensure that models generalize well to unseen data. Okay, so next we have evaluating classification models. Let's first focus on classification models. A powerful tools for evaluating classification models is confusion matrix, which follows the actual and predictive classification. True positive, correctly predicted positive cases. True negative, correctly predicted negative cases. False positive, incorrectly predicted positive cases. False negative, incorrectly predicted negative cases. Okay. From the confusion matrix, we can derive precision recall, F1 score, which gives us deeper understanding of the model performance, especially when the data is imbalanced. Okay, another important metric is ROC curves, which plot the true positive rate versus the false positive rate at various thresholds. The AUC, area under curve, measures all the overall ability of the classifiers to discriminate between classes. The higher AUC, the better the model is. Okay, so next we have evaluating regression models. For regression problems, we use different evaluation metrics. This includes mean absolute error, mean squared error, root mean squared error, root squared error. Okay, so mean absolute error, the average absolute difference between predicted and actual values is given as an idea of the error magnitude. Okay, in mean squared, the average square difference between predicted and actual value. It penalizes larger error and more heavily root mean errors. The square root of the MSE, it is in the same unit as the target variable, making it easier to interpret it. Okay. Then we have R squared. This is a proportion of variance in the target variable. This is predictable from the input variable. A higher R2 square value indicate a better fit of the model to the data. Okay. Let's have hyperparameter tuning overview. So now let's talk about hyperparameter turning. Hyperparameter are parameters that control the training process, but they are set before the model training begins. For example, a random forest model, a number of trees is a hyperparameter. Parameter, on the other hand, are learned from the data during training. Example, weight in a neural network. Hyperparameter turning is a crucial because it can diametrically affect the performance of your model. Even a good algorithm can perform poorly if hyperparameters aren't set correctly. So, turning these hyperparameters is essential to optimize the model. Next, we have techniques for hyperparameter turnings. So, there are few techniques from which we can for the hyperparameter turnings. First, we have grid search. Okay, grid search. This is a brute force approach where we define a grid of the hyperparameters value to test. This model is trained and evaluated for every combination of hyperparameters. It is exhaustive but computationally expensive. Okay, then we have random search. Instead of testing every possible combination, random search sample a fixed number of hyperparameter combination at random. This can more efficient than the grid search, especially when dealing with a large number of hyperparameters. Okay, then we have Bayesian optimization. This method builds a probabilistic model of the objective function and tries to find hyperparameters that maximize it. It's more effective than grid and random search for a large scale problem. Okay, then we have next we have okay. Like So that's it for the video. To conclude this, I would like to say that model evaluation and hyperparameter turning are essential steps in building a high-performance machine learning models. By evaluating your models with various metrics like accuracy, precision, recall, and other, you can excel effectively. And through techniques like grid search, you can optimize the model hyperparameters to improve its performance. Experimenting with different evaluation metrics and turning techniques will help you to build robust models that generalize well to unseen data. Okay, in the next video, we will discuss an advanced topic in machine learning and explore techniques like assemble learning and neural network. See you there. Thank you.